Here's just a few additional example problems with momentum and impulse. So our first problem is this. A car with a mass of 1,500 kilograms is going due north, or the plus y direction, at 15.5 meters per second. It then slows down and stops at a light. Next, it turns right and speeds up such that it is then going due east, the plus x direction, at 12.7 meters per second. What is the total impulse that the road gave to the car during the course of this story? Okay, so here's our diagram. I initially have a car which is going north, going in the plus y direction with an initial velocity and a mass. And then it stops, turns right, and speeds up again so that it has a final velocity which is going in the plus x direction. And our objective is to find the impulse that the road gives to the car. Our givens are the mass of the car, the initial velocity, which is in the j hat direction, and the final velocity, which is in the I hat direction. Our basic equations are, first, we know that impulse is just the change in momentum. There should be a vector sign over that delta p. I forgot that. And we know that momentum is just mass times velocity. So our symbolic solution, the impulse is just the change in momentum, which is just the final momentum minus the initial momentum of the car. But the final momentum is just mass times the final velocity, and the initial momentum is just mass times the initial velocity. So there's our solution. Now we just need to plug the numbers in. Mass is 1,500 kilograms, and then of course V final is 12.7 meters per second in the I hat direction, and V initial is 15.5 meters per second in the j hat direction. We just multiply that out, and we get that the impulse that the road gave to the car is 1.91 times 10 to the 4th kilograms meters per second in the I hat direction, minus 2.33 times 10 to the 4th kilograms meters per second in the j hat direction. And the units, oh, I forgot to do the units section, but the units do work out. It's kilograms times meters per second, and those are the correct units for impulse. Gauge and guesstimate, well, you probably don't have a really good feel for what's a reasonable impulse, but you know, it's not like a billion, so I guess that's okay. Limits, trends, and known cases. Well, if we look at this, if m gets bigger, if we have a bigger car, it should take a bigger impulse to get it to make that change. And that's in fact what our equation says. If Vf is bigger, we would expect the impulse to have a larger positive x component. If the final velocity is in the x direction, and so we have to give a bigger x component of impulse if we want to have a bigger final velocity. On the other hand, if the initial velocity is bigger, that's in the y direction, and we have to get rid of that y component as part of our impulse. And if v initial is bigger, we expect that we should have a larger negative y component of our impulse. And of course, if the two velocities are the same, we expect the impulse to be 0, right? Nothing happened, and that's what our equation does as well. So it looks like we probably did this right. Here's our next problem. A child with a mass of 34.5 kilograms is swinging on a swing. At their highest point, they are 1.5 meters above their lowest point. What is the magnitude of their momentum at their lowest point? Well, here's our diagram. Let's let y equal 0 be the lowest point in their swing. And the child has a mass m, and at their highest point in their swing, they're a distance h above the lowest point. Now our objective is to find the magnitude of the momentum at the bottom. And we're given the mass and the height, and we know that gravity is 9.81 meters per second squared. Our basic equations are, first of all, definition of momentum. Momentum is mass times velocity. The potential energy due to gravity is just mgh, and kinetic energy is 1/2 mv squared. And then conservation of energy Since gravity is a conservative force and the force of the chain on the swing doesn't do any work because the force is orthogonal to displacement, then we expect energy to be conserved, such that K initial plus U initial equals K final plus final potential energy. Okay, for our symbolic solution, we just say, look, what we're trying to find is the magnitude of momentum, which would just then be m times the magnitude of velocity. So I need to find the magnitude of velocity. To do that, I'm going to use my conservation of energy equation, and our initial kinetic energy is 0. When we're up at this highest point, we're not moving. Our initial potential energy is just the potential due to gravity, mgh. Our final kinetic energy is just 1/2 mv squared, where v is our final velocity. And our final potential energy, because we defined the lowest point to be y equals 0, the gravitational potential energy there is 0. So now I have an equation I can solve for v. The first thing I'll do is I'll get rid of the zeros, divide both sides by m, and I get this equation here. If I just multiply both sides by 2 and take the square root, I get the velocity. So velocity is the square root of 2gh. I plug that into my equation to find the magnitude of the momentum. It's just m times that, and there's my solution. Pretty straightforward. All right, to do my numerical part, I just plug in the numbers, and I get 187 kilograms meters per second. Units, well, my units are kilograms on the outside of the square root, and then I have meters per second squared times meters, which is meters squared per second squared. Take the square root of that, and I get meters per second. So it's just kilograms meters per second. Those are the units of momentum, so the units worked out. Gauge and guesstimate, once again, probably don't have a feel for what's a reasonable momentum for a child in a swing. But, you know, it's not a billion. That's good, right? So we'll say we're good with gauge and guesstimate. Limits, known cases, and trends. Well, let's look at this. If the mass of the child goes up, we would expect to have more momentum, and that's what our equation says. If gravity were bigger, we'd expect to have more momentum at the bottom, and that's what our equation says. If the height change is bigger, we would expect to have more momentum, and that's what we see. And you know, if gravity were 0, velocity wouldn't change as you go down, and you'd get 0 momentum. If the height change were 0, you'd get 0 momentum. If the mass of the child is 0, you'd get 0 momentum. So our equation seems to follow the trends that we expect and the limits that we expect. So we probably did it right. Okay, now let's do one last quick problem. I place a block with a mass of 2 kilograms onto a spring with a spring constant of 185 newtons per meter. I push the block down, compressing the spring such that it is 11.2 centimeters shorter than its relaxed length. I then let go of the block, and the spring launches it straight up into the air. What is the block's momentum when it reaches its highest point? Okay, this looks like a complicated problem, but really all we have to do is say, well, when it reaches its highest point, that's when its velocity is 0. A momentum is mass times velocity, so if the velocity is 0, the momentum is 0, and we're done. All right, I hope you enjoyed this video. I hope it was useful for you.